Oh, yes, hello, everybody. Yeah, I said chapter 2 is going to be pretty short and sweet. It's only got 4 sections in it. Section 3 will be done at the beginning of chapter 5 when we start dealing with compound functions. All right, so we're going to do sections 1, 2 definitely today, and sections 4 and 5. Section 1, we started doing this last week a little bit. Increasing, decreasing functions. We look at maximum, minimum. Only thing we didn't do is piecewise define functions. So we'll go through that real quick. Then in section 2, we're talking about the algebra of functions. All that means is we can add, subtract, multiply, and divide functions together. Then we're going to look at domains of those functions. And then we're going to end up that section with the difference quotient. And actually, this is a pretty important thing because, again, if you're going to go on further in mathematics, this is the basis of calculus. This is where calculus, in the first part of the class of calculus, you discuss this again, and then you go off from there. So you guys will know as much as Calculus 1 students at the beginning of the semester. Then we'll talk about symmetry of functions. And then if they're odd, even functions. Last section will be on track section 5, transformations. This is where you need to know the library of functions. Because the better you know those 12 functions, the easier that section is going to be. All right, as I said, we discussed a little bit in section 1. Increasing, decreasing, or neither. An increasing function looks like this. This is your function f of x. That's increasing function. A decreasing function looks like this. And if it's not increasing or decreasing and it's a function, it could only be a horizontal line. Which we call it being a constant. So let's look at what the definitions say about an increasing function. We have 2 points on the graph. The first point belongs to x1, y1. And the second point belongs to x2, y2. x1 is less than x2. If you put the points, no matter what points they give you, if you put the points where the first x is lower than the second x, rearrange them, then if y1 is less than y2, the function is increasing. So you always put them in x1 being less than x2. For example, if I gave you the points 3, 7, -2, -10, is that line increasing or decreasing? The easiest way to do it is look at the x's. Which one's smaller, 3 or -2? So put that one first. Put that point first. And then put the second point. Rewrite. So x1 is less than x2. Then compare y1 and y2. Because this is x1 now, this is x2. So this one is now y1, this one is now y2. So is -10 less than 7? Yeah. So it's increasing. If you're given a graph, it's easy to see if it's increasing. How can you tell the graph is increasing? It's going up, yeah. Because remember, x's always get bigger. So as x gets bigger, the line's going up higher, higher, and higher, and higher. That's increasing. Another way you can do is if the graph is increasing, you can plug these 2 points and that number will be positive. You can find the slope. So if the slope is positive or the graph is going up, or as x1 is less than x2, y1 is less than y2. All these conditions mean the same thing. Now let's look at the second one. Same thing here. We have a point x1. And then we have another point at x2. You have 2 points, x1, x2, y1, y2, where x1 is less than x2. Then if y1 is greater than y2, the function is decreasing. Here are 2 points. So we do the same thing. Look at the x1, x2. Is x1 less than x2? No, so we switch them around. So we have -2, 10, 3, 7. Rewrite it so x1 is less than x2. Then compare y1 and y2. So we have 10 and 7. Is 10 bigger than 7? Yeah. Then y1 is bigger than y2, then it's decreasing. Or if you plug them into the slope, you would get a negative number. So those are 3 ways you can determine whether a function is increasing or decreasing. You can look at the graph. If it's going down, as x gets bigger, the graph is going down. That's one way. Rearrange them so you have x1 is less than x2, and then look at the y values. Or you can plug them in the slope formula. And if you get a negative number, then the answer, it means it's a decreasing function. Okay, now we have 2 values here, x1 and x2. And they both belong to the same y value. And to keep things constant, then we'll always say that x1 is less than x2, which is really, for this, you'll see it's not even necessary. Then if y1 equals y2, the function is constant. So if you notice that the x's are different and the y's are the same, then you know it's constant. But following the same logic, let's put x1 being less than x2. That way we don't have to learn anything different. Then compare y1 and y2. 7 equals 7. It's a constant. If it's a constant, then the slope equation will equal 0. So far, so straightforward. Let's look at an example. Here's the example. Determine the intervals in which the function in the figure below is increasing, decreasing, or constant. Now, I didn't tell you this earlier, but when you determine the intervals, whether the function is increasing, you only report on the domain values. In other words, the x values only. And 2, the interval notation will never have brackets. You only use parentheses. Because we don't know what happens at endpoints. And I'll show you why in a second. So looking at this, let's figure out where it's increasing, where it's decreasing, and where it's constant. So starting from left, going to the right, let's look at an answer. What's the first segment of the graph doing? Yeah, the first segment of the graph is on this side. It's going down. How do we know it's decreasing? Because as our line is increasing, the graph is going down. So it starts off from where? Because the line has an arrow, it starts off at negative infinity. So it's decreasing from negative infinity to where does it stop decreasing? -1. That's where it stops decreasing. What does it start doing at -1? Right, so it's constant from -1 to where? Very good. To 3. Then from 3, it's doing what? So it starts off at 3. It's increasing to where? And then at 5, it does what? So it starts off at 5, and it's decreasing to where? Positive, right? And since we're doing interval notation, we have to put a union in the middle of in the decreasing part. If you notice, as we're going from negative infinity to -1, then we jump over here to this -1. Then we go from 3 to 5, and then we jump from 5 to here. So you always have to have, you can't have any holes. Everything has to be connected. This one starts at negative infinity, goes -1, -1 to 3, 3 to 5, 5 to infinity. So you have to have that overlapping. That's why you can't have a closed interval at that point. Because if you had a closed interval, then the other interval couldn't use it. So far, so good. While we have this picture up, let's look at this value here. Point 52 is called a vertex. That's singular. In plural, it's vertices. I'm jumping ahead a little bit, but while we're here, a vertex can be the highest point that's called a maxima, or it can be the lowest point. And that's called a minima. So at 5.2, is it a maximum or a minimum? Well, yeah, it is a maxima for this area. Is it the highest of the overall picture? No, because this point goes up higher. So we call point 5.2 a relative maxima or maximum. Relative means only for a short interval. So a relative maxima is only for a short interval. So it's the highest of this little thing here. It's the highest of this little part right here. If it's the largest of anything, if the point is the highest or lowest over the entire domain, then it is called an absolute extrema. Max if it's highest, minimum if it's lowest. Yeah, I'm using a lot of Latin words here for you. Extrema, first time using the word here, extrema simply means it's a vertex. It's the highest or lowest point. So these are extrema. Whether they're relative or absolute, it all depends on the function itself. But we're gonna do some examples of that in a little bit. Let's look at another example here. Use the graph below, determine any relative maxima minima of the function. We're going to get to a point where all I have to do is give you that. And you can tell me what the graph looks like. And you can actually graph the picture. In chapter 4, we'll get to that point. But right now, if you memorize the functions in the library of functions, you can tell me the basic shape of this curve. Just by looking at this function. This part here tells me, since it has a cubic function, we know the graph will look like this. If you look at your library of functions, that's exactly what it tells you. A cubic function, so that's the biggest exponent, So we know we have that shape. We also know that this is going to be our y-intercept. The constant is always a y-intercept. Y equals mx plus b. The b is a number. So it's a constant. It's always the y-intercept. So between here and there, the only things we have to figure out is how to figure out the x-intercepts. That will come up in the near future. But for this one, all I want are the relative maxima, minima. So let's see, relative maxima, relative minima. Okay. So what are our relative maximimas? Where's the relative maxima? Which one? Right. At this point, it's at negative 0.082, 2.004. That's our relative maxima because it's the highest point of this area right here. The relative minima is the lowest point. That's at 4.082, negative 1.604. That's part A. Part B is tell me where it's increasing and tell me where it's decreasing. Where is it increasing? From where? 0.282? Okay. Is that the only place it's increasing? Look at your pen. If you're, does the graph go up at any point? From where? It goes, but this is an arrow. That means it goes on, so it goes to negative infinity. So the increasing starts at negative infinity, keeps on going all the way up to negative 0.082. Remember, only report the x values, not the y values. When you're looking for increasing, decreasing, only report the x values. And at negative 0.082, what's it doing from that point? It's decreasing from negative 0.082 to where? To 4.082. It's decreasing. And then what's it doing at 4 point? To where? Yeah. So then we union this one with 4.082, comma, infinity. Any questions? I mean, if you came in late, if you have any questions, please shoot away, ask questions. We know the function's increasing or decreasing by looking at the slope of the equation. The slope of this part of the equation from negative infinity, if it's going that way, it's going up, it's positive until there. What is this point called? It is the y-intercept, but what is it called in this? We're talking about increasing, decreasing graphs. What's that? Which one? This point here, what's that location called? We said it's right, yeah, it's the y-intercept. But okay, then what's this number? What's this number called? I get away from the intercepts. We're not talking about intercepts here. We just talked about it. Well, it's with each part has a slope, but that's not what this point is called, or this point. Yeah, this is called the relative maximum because it's the highest. This is called the relative minimum. This is the relative min. These are vertices. The points at the very top or bottom of a curve are called vertices. These two are called the vertices. How do we know they're vertices? There are two ways. What's the slope of the vertex? Think of a roller coaster. When you're at Six Flags and you go on a roller coaster, it's one of those that goes up and down. When you start going up, before you start going down, what happens to that roller coaster? Well, it slows down, but look at the slope of the roller coaster. What's happening at that point? It's constant. Its slope is zero, and then it goes to negative. So at these points, the slope is zero. At the vertices, the slope is zero. Let's look at slope. Since we're talking about slope, increasing, decreasing. At the relative maxima, let's say we had a relative maxima. So it looks like this. The slope is zero. We'll call that point A. How do we know that is a maximum with respect to slope? How do we know that point A is a relative max? Remember, the slope is zero at that point. What's happening to the left of them? Yeah. The slope is positive. It's increasing. To the left of it, the graph is increasing. So the slope is positive. It's increasing. And then on the other side, what's it doing? It's decreasing. So that means the slope is negative. Think of the number line. If we're going from positive numbers, 3, 2, 1, and then we go to negative numbers, what has to be in the middle? 0. So if we're looking at slope, it's increasing, it's getting shallow. All of a sudden, it goes to 0, then it starts going down. That's how you know it's a relative maximum. So the slope is negative, and it's decreasing. So to the left, it's increasing, and to the right, it's decreasing. Therefore, it's a maximum. At the relative minima, we'll call that one B. The slope is 0. So what's happening to the left of it with the slopes? Yeah, the slopes are negative. It's decreasing. Slope is negative. It's decreasing. And then to the right, the slope is positive. It's increasing. So that's how you can tell them apart, what's going on. What do y'all think? First, once you see it, it makes sense. Now, for some reason, the chapter takes a horrific, terrible turn. We now go to application problems. What do application problems mean? Word problems. Application problems. These are just another way of saying word or real world examples. There are 4 parts to solve these problems. After you read the problem, identify the information given. Identify, in other words, what values are given. How do they relate to the problem? What is the problem asking for? What is it asking you to find? How do you know when you're finished? Step 2. Draw a picture if possible. Or just a sketch of what it's trying to tell you. Determine the formula required to solve the problem. somewhere in the words, it's going to tell you, it's going to give you a hint of what kind of formula you're going to need. Find the relationship between the values given and plug them into the formula. And then solve. Okay. So those are pretty much, yeah, we could put it into 5 steps, but these are pretty much 5 steps. Find out what's given to you, find out what they want, find out what you have and what you need, and then put it all together. All right. Let's look at an example here. Two nurses, Kiara and Mateus, drive away from a hospital at right angles to each other. Kiara's speed is 35 miles an hour, and Mateus's speed is 40 miles an hour. Express the distance between the cars as a function of time dt, and then find the domain of the function. So step 1. What's given? In that those 2 lines on the very top, a lot of information is given. We have 2 people. We have Kiara and we have Mateus. And then what? They're at right angles from each other, from a hospital. So that tells us 2 things, actually. They both leave from the same place. They both leave from the same hospital. What does right angle mean? Very good. This means 90 degrees. So if Kiara is going that way, that means Mateus is going this way. And they have a 90-degree angle between each other. Do we know anything about Kiara? Yeah, she's going 35 miles an hour. And Mateus is going 40 miles per hour. So here's our step 1 and step 2. We drew a picture of it. Step 3 is, what kind of formulas do we know about this? There are 2 different types of formulas that we have to know about this. Do we know any right angle formulas? Do we know any right angle formulas? A squared plus B squared equals C squared. What's that called? Pythagorean theorem. If you think about it, that's what we have here. Here's Mateus, here's Chiara. And this is the distance apart from each other. So we know that the distance between them is going to be Chiara's speed squared plus Mateus's speed squared. Now input speed here. That stands for speed. There's one more formula we need to know. Remember in the formula, it said here in the question, it wants the distance in times of t. That's what this means. Distance in time t. So that's the only, in other words, t is the only variable that we have. So since it says distance, the distance formula equals rate times time. That's the distance formula. Again, this equation gave us two formulas without specifically stating so. So what we have here, it's a distance with respect to time. So the distance of Chiara with respect to time, her time, plus the distance of Mateus with respect to his time. The good thing is they both left at the same time. They didn't tell us that they left at different times. So it means we don't have a t plus 3 or t plus whatever. We just said they both have t. So what is the formula for Chiara with respect to time? We have rate times time squared plus rate times time squared. What is Chiara's rate? And Mateus is 40 times t squared. Because notice t is the only variable in there. So to find the distance, what do I have to do now? Do I want distance squared or do I want distance? I want distance, so I have to get rid of the square. How? Square root both sides. So the distance between Mateus and Chiara are 35t squared plus 40t squared. And there's our answer. So far, so good. Again, it just takes practice. It just takes practice. Oops. And here's another example about an office problem. A community college has 30 feet of dividers to set off a rectangular area for a student testing center. So they have 30 feet of dividers. For a rectangular student testing center. Student testing center. If a corner of the math lab is used for the testing center, so here's the math lab. If a corner of it is used, the partition only needs two sides of the rectangle because this is a wall and this is a wall. So that means the partition only has to be this and this. Express the floor area of the office space as a function of the partition length. So what formula is A asking for? Yeah, it said area. What's formula for area? Right, base times height, base times width, or length times width, doesn't matter. Let's put length times width. Length times width. So this will be our length, this will be our width. Now, how do we connect these two? We have W and L. We have to get down to one variable. How long is L? Do we know? So we say it's X. It could be X feet. Remember, how many feet do we have to work with? 30. So if there's X feet, how many feet are on W? You do know. Think about it. You just told me you had 30 feet of material. If I use X feet here, how many are left? You have 30. You take away X, whatever's left is over there. So if that's 10 feet, how much is over here? 20. Yeah, so it's 30 minus X. So we have the area is X times 30 minus X. I mean, it's a pretty simple concept, but then if you've never seen it before, if think about it, if I have a foot-long piece of chocolate and I cut off 6 inches, let's say if I cut off 6 inches, how many inches do I have left? 6. So it's whatever I cut off, take away from the whole foot, whatever's left is what you get. So that's what that means. Because both of these, if I add them together, have to equal 30. That's the perimeter. So this becomes, from here, this is part A. That's question A. That's our formula for area. Yeah, we could multiply them together if you want. X times 30 is 30x. Positive times negative is negative. X times X is X squared. We can say that's the formula. But for B, is saying what's the domain of our function, A of X? What's the smallest it can be? Think about it. If you had a picture here, what's the smallest this length can be? What if the whole thing is just put against the wall? The smallest it can be 0. What's the largest this one can be? Yeah, the largest it can be is 30. Anything else between there, now I have some room. Because this one is against the wall or against the wall. You notice how these answers, if I take both of these and set them equal to 0, what do I get when I solve them? X equals 0, got that. 30 minus x equals 0, add x to both sides. So 30 equals x. We got our domain from our function. We set them equal to 0. Now, okay, the last one says graph our function. We know two things already. We know the smallest it can be is 0, because this is x and this is area. What's the largest it can be? 30. So we know it has to stay in that domain. What does this kind of graph look like? I asked you all over the weekend to look over the library of functions. What does the x squared function look like? It's the parabola. But since it's negative, it opens down. So it looks like this. So the largest area is going to happen at that point, which is, in this case, we're lucky because these are our two x-intercepts. What number is halfway between 0 and 30? So the maximum area is when the sides are 15 feet each. So whenever you come up with an equation for your function, if you graph it, you can see the maximum or minimum. So the highest point is going to be the maximum area you can find, which is, I kind of gave it to you here. Here's your domain, 0 feet to 30 feet. If I plugged in halfway between there, that's the highest point. It's going to be at 225. So to get the maximum area of our testing center, we need 15 by 15 feet. Okay with that? Again, you just have to practice word problems. Piecewise defined functions. Is when a function is divided into two or more subfunctions within the domain. like we did earlier, remember when we look for increasing, decreasing, every point on the x-axis has to be accounted for. That's what this thing has to do. For example, this is what it looks like. Let's say f of x is a function so these are my y values. These are my x values, the domain. What this function looks like actually is this. For this function, we use that equation when x is less than -2. Use this function and then we use this function, f of x equals 3, when x is greater than or equal to -2. First, check to see if all the x's of the domain are all real numbers from -infinity to +infinity. X is less than -2, which goes from -infinity to where? -2. That's what this one says. This one starts at -2 and then goes to +infinity. So this one goes from -infinity to +infinity, which is all real numbers. We cannot have a hole anywhere in the domain. It's got to be a continuous function. So draw each subfunction on the same graph. So we make our chart. So the first graph we draw, f of x equals x plus 2 on this domain, -infinity to -2. These are my x's. What kind of graph is it going to be? What's it going to look like? What does x plus 2 look like? It's a linear equation because x doesn't have any special operations or exponents or something in the denominator. It's a linear function. We know it's a line. So always start off with the point in question at -2. So at -2, if I plug it in there, I get -2 plus 2 is 0. So at -2, we get 0. So at -2, Is it an open or closed circle at that point? It's open because we cannot use -2. Okay, remember, x is less than -2. So at -3, if we plug it in there, -3 plus 2 equals -1. So at -3, it's -1. So we know these lines, since it's a linear equation, it goes on forever like that. That's the first graph. The second graph is f of x equals 3 whenever x is greater than or equal to -2. This is the x and this is the y. So I start off with the endpoint, -2. When x is -2, what's y? 3. It's a constant. When x is -1, you go bigger. It's 3 also. It's a linear equation. It's a constant equation. So at -2, the answer is 1, 2, 3. It's a solid dot there. At -1, it's 3. So from there, it goes on forever. That's a piecewise defined function. Because it's been defined in multiple pieces. Any questions? Now, if you need me to go back on any pages, tell me. I mean, I really don't mind. I'm sorry if I go too fast. Get it? No questions? Okay. I see a lot of blank stares, like the truck's gonna hit that deer. Let's look at this example. Let's do two things here. Let's first go ahead and answer these questions, and then let's graph this one. So A, it says find f of -5. So I'm gonna call this first one A, then B, and then C. So which formula do we use for this first one? What equation? A, B, or C? Ah, how do you determine which formula to use? What is my x in this question? X is -5, right? It's whatever's inside there is x. So is -5 less than -2? Between -2 and 3, or greater than 3? It's less than -2. So I have to use this equation. I plug in -5 plus 1. 5 is bigger. 5 minus 1 is 4. So the answer is -4. B, at f of -3. Which formula am I using? A, B, or C? The formula depends on what your x value is. What is my x value in this one? X is -3. So where is -3 in there? A, B, or C? A. Because -3 is less than -2. So I'm using this equation again. X plus 1. So it's -3 plus 1 3 is bigger. 3 minus 1 is 2. C, f of 0. Which formula am I using? A, B, or C? Why B? Well, yeah, because 0, we're looking at x equals 0. 0 is between -2 and 3. So we have to use this middle one. So it's 5. So the answer is 5. It's a constant function. At f of 3, which one do we use for f of 3? B, because B goes from -2 to 3 inclusive. So 3 is included here. So it equals 5 also. And that's our answer. F of 4, A, B, or C? C, yeah, because 4, we have x equals 4, and 4 is bigger than 3. So we have to use this one, x squared. So it's 4 squared equals 16. And the last one, f of 10. Yeah, because this one, our x value is 10, and since x is bigger than 3, it has to be this one. So it's 10 squared, which is 100. So far, so good? Now, what do those numbers we just found, what do those represent? What do they represent? What's that? No, actually, we know the domain. We have to check. Well, I'm glad you said that. Is the domain from negative infinity to positive infinity? Yeah, it goes from negative infinity to -2, -2 to 3, and bigger than 3. So it's going. Our domain is negative infinity, positive. That's good. But no, these numbers do not tell us our infinity. We've done it in chapter 1. What do these represent? Remember, f of x is the same thing as y. These are all points on a graph. This first one, let me block these off. This first one, the x is -5, the y is -4. That's the point. And the next one, x is -3, y is -2. That's that point. Zero, 5. Do the last 3 for me. What's this one? 3, 5. Next one is 4 and 16, because whatever's inside the parentheses is your x. Whatever the answer is your y. And this one is 10, which these are all points on a graph. So in other words, if I gave you a graph that looked like this, I could ask you questions like this. If I asked you this, what would be the answer? Okay. Nope, because there's 5. What does 5 represent? This is your x. So if you go to x to 5, where does that point lead to? -1. If I gave you this, what's the answer? X equals 1. Because, yeah, I gave you the y value. Where does that go to there? It belongs to 1. So you'll have questions like that as well. Or you can have questions like that. So if I give you the graph, you can work backwards. Yeah, we have 2 more questions here that deal with graphing, so we'll do these 2 instead of that one. So remember, points on a graph are x and y, which also means x f of x. So if I gave you the f of x, if I give you the y value, tell me what the x is. If I give you the x value, tell me what the y is. All right, let's do 2. You need to back up there? Okay. And we'll do 2 pictures that deal with graphs, and then we'll call it a day. Okay. And I do apologize if I go too fast sometimes. It says graph the function defined. When you do this, first look, what kind of graphs are they going to be? What kind of equation is the first one? From the library of functions, what kind is it? Look at the x. Does it have anything around it? Above it? On it? No, since it's x by itself, really, it's a linear equation. Think of y equals mx plus b. How about the second one? The same. It's a linear equation. It doesn't have any exponents or anything. So we're good there. As long as we know we have 2 equations, our graph is going to be much easier. Here's the first equation. G of x equals 1/3 x plus 3. This is good for x is less than 3. Since we know this is a linear equation, we only need 2 points. We only need 2 points. Our x's have to be less than 3. So the first one I'm going to pick, I always pick at the end point, 3. Since I can't use it, it'll be an open circle. I plug it in my equation. 1/3 times 3 plus 3. The 3's cancel, So we have 1 plus 3 equals 4. So at 3, we have a point, an open circle at 4. Why is it open? Because I can't use 3. I can start there, but I can't use it. What would be the next easy number to put in there? Remember, our x's have to be less than 3. Give me a number less than 3. That's easy if I put it in there. If you can use 0, use 0. Because 0 will make that go to disappear. So it's just 3. 1/3 times 0 plus 3. So that disappears. So it's just 3. So at 0, we have 3. And there's our graph for that side of the line. This is for x being less than 3. The next one is for the function y or g of x equals negative x. It's also linear, so I only need 2 points. This is g of x equals negative x. But now, my x values are greater than or equal to 3. So what's going to be my first number I put in there? Always start from the endpoint, 3. If I plug 3 in there, I get negative 3. Give me another number that's greater than 3. 4. If I plug it in there, I get negative 4. So at 3, I get negative 3. It's a solid dot because I have an equality. And at 4, I got negative 4. So there's that graph. So the idea is separate your two functions or the number of functions you have into separate equations. Find out what x values you can use. Always start from the endpoint. If there's no equal sign there, then it's an open circle. If there's an equal sign, it's a closed circle. One more. Let's graph this one. Because I have 3 separate equations here. I have 3 separate functions. The first one, f of x equals 4, when x is less than or equal to 0. The next one is 4 minus x squared when x is between 0 and 2. And the last one is 2x minus 6 when x is strictly greater than 2. So far, so good. Now I have to create my point charts. Those are my old tables. What do we know about the first graph? F of x equals 4. So my first number I'm going to use is that 0. Because that's where it tells you I'm going to start. If I plug in 0 for f of x, what do I get? It's a constant. It's always going to be 4. There's no x, so nothing changes. So another number less than 0 is -1. It equals 4 also. So at 0, since we can include 0, at 0, at 4, we get a solid dot. At -1, at 4, we get a solid dot. So it's a horizontal line. Because it equals 4. It's a horizontal line. The next one is a quadratic equation. Because it's x squared. X squared, the graph looks like this. But since it's negative, it'll be down. It's going down. This graph will look like this. So the first point I'm going to use is 0, because that's my endpoint. If I plug in 0 for there, I get 4 minus 0 squared is 4. So it's 0 and 4. Yeah, it's already a point there, so I don't have to do anything. Then next, I put 1 in there. 4 minus 1 squared is 4 minus 1 equals 3. So when x is 1, y is 3. And then 2. 4 minus 2 squared is 0. This is a curve, so it looks like this. And I know that at 2, since I put an equality, I could put a solid dot there. And the third one, I start off at 2, but it's going to be an open circle. I plug in 2, so it's 2 times 2 minus 6. 4 minus 6 is -2. So at 2, it's -2. Open circle. A number bigger than 2, I'll put 3 in there. So 2 times 3 minus 6. 6 minus 6 is 0. So there's a dot there. There's my graph. You have 3 small, however many functions, the equations there are. You have that many small graphs to put on one picture. That's all this section does, deal with that. But I can't stress enough, start memorizing the library of functions. Because once you start, you understand what the graph's going to look like, you know what you're going to be dealing with, what your picture is going to look like. I knew that this one's going to be a horizontal line, since it's 4. I knew this is a linear equation, it's going to be a straight line. This one's a curve, because it's x squared. So that kind of stuff will help you draw pictures. All right. So unfortunately, we just got section 1 done, if I'm not mistaken. Let me see more on functions. Yeah, we haven't gotten to the algebra of functions yet. Yeah, we'll try to do it next time. Worst case scenario, next Monday we finish this chapter. All right, everybody, have a great, safe day. Do your homework.